Welcome everyone. This is Daniel Howard. I'll be presenting today a hands-on session using OpenACC and MPAS-A, the model prediction across scales and atmosphere core model developed here at NCAR and various other labs. So today we will be exploring that model MPAS-A and applying techniques we learned from the previous sessions where we used many weather and implemented various OpenACC GPU program paradigms for developing for GPUs. So we'll review some of those exercises from that prior session, and then we'll get into MPAS-A and discuss that model's approach towards porting its large-scale models for running on GPU clusters. So again, be sure to set up a Jupyter Hub portal instance and update your materials to today's content. If you have any questions or issues navigating that, feel free to message in the chat, and we'll be sure to have someone support you in that matter. So from the notebook page, make sure on the first cell that you see right near the top of the notebook to run that cell so you populate your project code and Q code. To note, we will want to change the queue to GPU workshop during the workshop, and the GPU type to GPU 100. That will allow us to use resources that have been reserved for us during today's session. Getting into reviewing the mini weather performance optimization we did at the end of the last session, predominantly it was suggested that we use the async and collapse clauses in order to achieve optimal performance. We then suggested a particular domain size in order to do some further testing and see if we could make some improvements on that. And one particular kernel that I ended up focusing on as part of the exercise, and hopefully you did too, was the semi-discrete step subroutine and a kernel within that function. Essentially, I have here the printout from the NV compiler AC time environment variable when you enable that with the compiler. And that provides some statistics on this particular kernel that I ended up analyzing. So in this case, we see that from that this fragment of the statistics output, we have the name of the subroutine which is analyzing the time it took on the device, the time it took on the CPU side. To note, that can be not as accurate when you have asynchronous execution enabled, as well as then the arrangement of gain worker vectors, etc. In terms of grids and blocks, according to the profiler here, where you see right below the 257 kernel launched 924 times line, you have a grid and a block with entries there specifying the number of gangs, which is equivalent to the grid size, and then the block size, which is the number of vectors and worker threads assigned to each gang. Sometimes you'll see that block in terms of a number times another number, and that's essentially the vector length times the number of workers in that order. In this case, we had only one worker per gang, so there's only the vector length is relevant in this particular execution mode. So one thing I want to point out though, when we use that async mode, so this is essentially a profile using the NVIDIA Insight Systems profiler. We'll discuss this particular tool in a later session, but this is just a useful tool right at this point to see what exactly is happening across the whole model here. So we see here the top half of this screenshot being the timeline of the GPU kernels across runtime within Miniweather. And then lower section just gives some more detailed text output about each of those particular kernels as you step through them across the model. And you can see in the bottom right, you can even see then that grid and block section in terms of defining the number of gangs assigned, and thus then also the number of vector length for each block. It also shows you the theoretical occupancy. This is not super great, but admittedly it's acceptable for this particular case. We'd be more concerned if that was less than 50%. But really, you should, if you can, you want to aim for as high a number as possible there in terms of making sure you're using as much of the GPU as possible during the runtime of the kernel. That, however, is dependent on the size of the domain and the size of the problem you're actually running in the GPU at the time. But again, when we look at this, just that timeline portion, when we have the async enabled, we see that all these blue boxes, which essentially are the compute kernels, are running right after each other. And that's essentially enabled by the async clause, where it basically allows, specifying, all the different, the weights for just around where we need to wait, which is when the device and host transfers and the host to device transfers occur, which are the teal and pink boxes you see before each of those sections of code. So this section here, there's some device movement happening. Previously, the CPU side was waiting due to the usage of async for these transfers to complete. After they completed, it's then allowed to then start scheduling again new compute kernels, and it goes through the sequence there, and the GPU will then just chug along and run through all the remaining kernels until it hits another wait section where it needs to do another computation, a movement of data at the end here, and that cycle repeats. So essentially, it just allows contracting all the operations within right after each other without necessarily having to wait between each different kernel. Since, for example, if we did not have the async enabled, all these different clauses, you'd see on the CPU side here, we have weights that are automatically generated as each kernel is launched or each data movement is launched. And that then creates these gaps between each of these kernels on the GPU side. And there's this wasted time that occurs if it's not running in an asynchronous mode. So if you want to improve performance, you should really look into effective use of this asynchronous operation that's capability within OpenACC. Nonetheless, if you like, you may also, and if you have the extra wherewithal, you can download this NVIDIA Insight Profiler tool client right to your home machine. You can even download these profilers to look at yourself in your own time. So getting back to testing that particular kernel we were looking at earlier, recall that final exercise we had in that session. So we're basically going to be looking at that same kernel we're looking at, the semi-discrete step subroutine. I had set up, in this case, you were welcome to that exercise to use different domain sizes, but we had a 1024 by 512 grid. And then note that the num_vars variable that's in this loop, that this triply nested loop that we were looking at, is a set value of 4. And that's just the number of prognostic variables that we're analyzing across Miniweather. So in this particular exercise, before I go through some of the results of that, let's just double check kind of that process of how, sorry about that, of how we want to be working on this. So if we go back to that session very quickly, we can go down to the Miniweather section here. And we have this cycle of making the executable and then building it, letting it run on the GPU. And essentially, if we go into our source file here, we basically have this loop we're focusing on here, this section of loops. And we're going to do something similar with MPAS-A. I'm just showing you an example here for how this process works in Miniweather. So in this example, we had set up, I just decided to test out setting a gain vector level parallelism to the outermost loop, then a worker level parallelism to the middle loop, and the vector level parallelism to the innermost loop. Having done that, we can then run this let it build. It's already been built in this case. We can then submit a job to let it run, and we can then look at the profiler time output to see what exactly was happening for that particular kernel. So for the kernel that we were editing, we're looking at this 257 kernel here. We see it launched on a grid size of 4 and a block of 32 by 4, and the length of this is the vector length, and this is the worker length, a number of workers. These were automatically assigned and generated per what the compiler thought was best. However, this performance here is actually pretty bad compared to other examples we might try. So if we go back here, maybe try a different arrangement. Let's actually just get rid of these. Let's do maybe you want to try out the tile clause, and let's do 32. Let's do actually 128 by 1 by 1. That's actually not as interesting in terms of essentially what this is doing is splitting up the work groups into a size of 128 by 1 by 1 tile that's looped through, essentially of a vector length 128 on this innermost loop, and each of these middle and outermost loop are only a size of 1. So this is actually kind of equivalent to just saying vector length is equal to 1. But you're welcome to, well, I'll talk about further in some of the results from that exercise later about what different configurations will do. But when we do this particular configuration, we can then go back iteratively, pretty quickly, just remake the executable, have that done there. We see it recognizes this tile clause. It's now tiled in this different way as opposed to what it was before. We can rerun it, and then we can look for again that profiler output to see what changes in timing occurred for that option. So we see here before where we were in the order of taking around like 900,000 milliseconds or 0.9 seconds, microseconds, excuse me. We're now taking about 60,000 microseconds. So that's a significant improvement. And you can see there's actually many more gangs being launched at once. And this is really where we want to see some of these sort of improved performance happening, where the GPU is able to execute many games at once and thus then occupy a much larger portion of the GPU simultaneously in a concurrent fashion. And that allows for greater parallelism and speed and efficacy in processing the problem we're trying to work on in this case in Miniweather. So that's just an example of how that process works back in Miniweather. And so let's just look through some of the types of clauses that I tried out when I was testing through this particular kernel. So in this case, I just tried assigning gang worker vector parallelism and different combinations thereof. That's allowable by the compiler. I even also moved that num variables outermost loop to the innermost loop. This is essentially because I knew that num variables loop is only a size of 4, so it's not very significant in terms of being able to fill up a full vector. By default, if we just use kernels or we specify which is recommended using the collapse clause, we actually get an auto vectorized vector length of 128. And that gives a device runtime of about 60,000 microseconds. But using these other approaches, we see gang worker vector, gang assigned on the num-vars loop, worker on the z loop, and vector on the x loop. That ends up getting about 800,000. That's just what we did essentially in terms of the initial example I showed you. But then if we try maybe even a different one, a worker vector sequential loop where we had sequentially running the num-vars loops, just so small, that's even worse performance. Essentially, your question might be here, if for that particular example, when we use worker vector sequential, the grid size was 1 and block was 32 by 4, and that's the choices the compiler made. So we did not specify worker or vector length or gang length in that case. Essentially, we only have one grid launching at a time. And then it has to just kind of like run through sequentially relaunching that whole kernel in order to complete the whole work unit. That then makes that particular arrangement the least performant. And so anytime you see in the profiler output like a small grid size, etc., that's something you want to look into and try to address and fix. Because oftentimes you'll have poor performance results like this highlighted here. Say if we try out different vector lengths, we can also try out different vector lengths just differently from the automatically chosen vector length of 128 when we just use collapse clause without anything else. So if we try like 32, 64, 256, etc., you usually want to do in multiples of 32 since that's the warp size. These are the different performance metrics that we see for Miniweather. We can see that the compiler actually chose the most effective choice here, the vector length 128. But some of the other choices get pretty close to the same performance and probably are equitable in ways and really just kind of deviant and just divergent in measurement just from just statistical error and just so that there would be so much issue in this particular case in choosing say 64, 256, or 512, but the 1024 and 32 lengths are in this case not as performant. And this basically, as you explore these sort of like different configurations, perhaps you might find even better ones than what the compiler chooses. Sometimes you don't, and the compiler actually does a really great job. But depending on the computational cost and the amount of optimization you want out of your model, it might be worth it to explore some of these approaches towards improving performance. One question to ask here is just, do you in general trust the compiler to make optimal choices with middle direction? That's something for you to decide over time as you experiment with OpenACC. But nonetheless, as development of compilers has progressed, they have gotten better over the years with making pretty good choices for the programmer and without needing significant intervention. The last one I'll talk about is this tile clause. This one's just kind of interesting in the case of this kernel. So again, there are various arrangements we can choose for assigning the length of the tile and the size of the tile for each of the loops that were nested in that triply nested loop. Some are relatively similar performance, such as using the 32,1, num vars, which is essentially, if you take the product of that, that's about 128, and that's equivalent to the length of our baseline size of grid block size for each gang launched. So you can maybe understand why that one's had performed similarly well to the collapse clause. In this case, it did not actually end up improving performance, and that's sometimes just an experiment you might have to go through in terms of whether or not tile will improve in performance. Usually, as covered before, tile improves performance if there's a need to coalesce memory together so that you access sequentially. But nonetheless, some other examples are just interesting to point out here. Some usage of tile will produce incorrect results in the model. In this case, this was the 32 num vars combination or 128.4 num vars combination. You might want to think about why those particular combinations compared to the others were incorrect. In this case, again, think about the warp size that we have and the maximum allowed amount of concurrent threads allowed to be run on the GPU at the same time. That is for NVIDIA GPUs about exactly 1,024 threads. So you notice for those incorrect clauses, the product of those variables for tile is actually greater than 1,024. So this is an issue that, even though it allowed the compiler to actually still compile the code and think it was working through the problem correctly, in this particular case, when setting tile with a tile size greater than the amount of warps allowed, threads allowed per block, then you will end up getting incorrect results, even though they perform at a significantly faster rate than the other clauses. This might be an issue to point out with NVIDIA, or actually just common point in terms of thinking about the application of these particular clauses in terms of how they are behaving on the kernel we're running on. So this is a point to keep in mind in terms of, as you might be adjusting some of these clauses, there is a potential to cause error in your output, and that's something you want to double check as you are running through and doing some of these experiments with these different clauses you might try out. So moving on from that, I just want to give a brief overview of MPAS-A. So MPAS is the model prediction across scales, and specifically there's the GPUized version, which is specifically focused on the atmospheric core of MPAS. So far, only the version 6 of atmospheric core has been ported to GPUs. You can feel free to refer to the website and or the GitHubs, as well as in the currently in development merge v7 version of MPAS-A. If you like, there's also an MPAS Ocean core that has some work being done on it in the past. There's an old presentation you can refer there. But nonetheless, it's a work in progress still in terms of getting MPAS to at an acceptable performance level for production level codes across different systems. So if you'd like a more complete overview of MPAS, I won't have time here to go into too much detail. It's a very large model. Feel free to look into the 2021 MPAS virtual tutorial, and consider looking at the upcoming joint WRF MPAS workshop. So MPAS is a fully compressible non-hydrostatic equation written in flux form. Basically, if you look through the code and the documentation, this is essentially what it's doing. There's a split explicit time stepping by third order Runge-Kutta. You'll keep in mind the third order Runge-Kutta method was the exact same that we use in mini weather, but this is just used in a much larger scale model. So in the case of the particular kernel that we will be looking at the end of the session, we will be looking at a solver that computes coefficients for vertically implicit gravity wave and acoustic computations. This is needed within each Mpassa time step. If you want to look more into this particular science and numerical physics about that implementation, feel free to reference the overview of within the 2021 tutorial previously referenced, or there's the AMS paper linked at the top of this page for more info. So in approaching porting MPAS to GPUs in the first place, Raghu Kumar was one of the main developers that helped support that process. And here's his recommendations on the basically cycle of development that should be considered when approaching a GPU refactoring project. So in this case, you want to start with developing a baseline for your model, and then move on to then actually porting, adding OpenACC directives. Then you want to be optimizing your model, which is what we probably be focusing on today. And then we want to do a portability check, making sure you're actually meeting the needs and expectations of the tests that you need to integrate with, as well as other systems and expectations you might have in terms of like being able to still run the CPU version alongside this GPU version. Then lastly, once you're satisfied with that cycle of optimization and portability checking with adding ACC directives, you want to then integrate that into your verification and benchmark suite to then finally either restart the cycle again for further additional porting of other parts of the model, or move on to another code or different project. Essentially, just following this process just helps give you like a plan and minimize the different pain points you might have in thinking about how to navigate such a large-scale code project. If you think of it in these smaller steps that can help manage this appropriately, you might notice within this process, there's this tool called Encode Gen. That's an automated tool that NCAR has developed to extract various kernels for analysis, but we will not be going into too much detail for Encode Gen in this particular session. So again, as I just outlined from that slide, you want to be establishing a baseline, ensure working accurate configuration for the target hardware alongside your software you're working along your external software. Then you'll be porting the code, actually then adding the OpenACC directives. You might typically focus on first adding the kernels directive, using the more descriptive approach. And then as you go through the cycle of optimizing, you might then move on to changing those to kernels directive as you want to improve performance alongside a process of analyzing those kernels you're adding, as well as then ideally always profiling each time. We'll discuss using profilers at a later session beyond the text-based profiler within the using the NVXL timer environment flag. From there, you want to check portability expectations. Be sure to continue navigating the porting process, and sometimes that involves you might not have a set of loops or section of code that's easily portable to the GPU, and thus that may require some extra work in order to eliminate any GPU anti-patterns, such as using linked lists, which is not compatible as a data structure with GPUs, or maybe like global memory variables that are constantly might indicate excessive data movement if left to their own devices across the model runtime. So again, this is then left after iterating those middle three steps. You can then integrate those changes into your model and make sure that it adheres to your current benchmarks and verification suites. Make sure you might then want to record some data and such about the performance of the model in order to publish for later results. But nonetheless, utilizing a version control process and ideally a continuous integration process in this development paradigm will be highly recommended towards making sure you are successful in making sure and ensuring that you can achieve this in a relatively quick fashion. So for MPAS, when we did that initial baseline, that we see the amount of time spent in different sections of the code. Most is in the dynamics and physics sections, as well as then subroutines within the physics or microphysics. So essentially, through the development, different initiatives were planned to port each section to GPU. One particular interesting note to make on MPAS is that the radiation physics was actually left to stay on the CPU side. So in this case, we actually set aside on MPAS some amount of CPUs to run the shortwave and long wave radiation physics operations, and then ported the rest, everything else in the dynamics and other physics operations to the GPU. This allowed for a lagged computation of radiation, where the CPU was allowed to run the radiation physics, and then at the same time, the GPU would then be running not a radiation physics in a synchronous manner. It's slightly different than using asynchronous within OpenACC, where there's literally different CPU tasks assigned that are not connected to the GPU to running the radiation physics versus the non-radiation physics. And this is just a different approach that is possible towards still, in this case, utilizing the full capacity of your CPU while the GPU that it's attached to is still able to do significant work across the model. So one last thing I'll talk about is managing GPU data in MPAS-A. So recall that when using ACC kernels and running the compiler, you will get a list of variables that are needed to manage data movement for that region. So you'll see it's generating these implicit copy ins, copy outs, etc. These lists can be useful for leveraging your own data directives as you then go through the optimization process to manage appropriate and optimal movement of data between the CPU and GPU as you proceed in the porting process. So for example, say you have this section of code, you want to then, you want to port that to GPU. You might say first add the kernel directive. The kernels will tell you which data clauses need to be copied in and copied out. You can then add those copies and copies out and then do some further testing and integrations within your test suite, make sure everything works out the same. And as you then go through that development process, you might then later change that to a data present clause, where then actually you shift that data copy or movement to another part of your code that encapsulates multiple kernels, kind of like how we had in Miniweather, where we had the larger data region around all the kernels in the main time step loop. So in MPAS, this is a approach that Raghu had recommended in terms of using development in this model framework. Once we add the data present clause, basically that just tells that kernel there that data is already present on the GPU and does not need to move it. Of course, you as the programmer will need to make sure that there's someone else, somewhere else in the code, data has already been moved onto the GPU for you, or you might say have been relying on the GPU manage flag. But nonetheless, if you want optimal code, it's important to be thinking about the where your data is resident on throughout the runtime, and you don't necessarily have to have all the data in the correct place right from the get-go. If you do the initial port just using ACC kernel and then the data movement around each of those kernels, it will be significantly slower, but it will at least be an iterative process that at least guarantees working of your model. And you can just check which kernels, say, as you develop, are introducing bugs or not, and then fix those bugs. And then as you then fix those bugs, you can then move the data movements to where you actually desire within the larger scale model. As those kernels were ported, basically those GPU, the CPU and GPU data copies were then moved to the initialization section of the model of each of the variables using the ACC declare create clauses, and then using unstructured data regions using copy data, enter data copy in prior to each kernel call. So if you click those links there, you can then see the approximately the types of where the data movement is actually happening within MPAS if you want to get a sense of how that works within the larger scale model. However, we will not be focusing too much on data movement in terms of the exercise we have later on. But nonetheless, this is the approach that MPAS chose to take, and it's something that you might consider in terms of thinking about navigating yourself the same. Keep in mind, when we talked about reference counters previously, even though the data copy in call is placed very frequently across the code, that copy in will still only copy in whenever those reference counters are going from 0 to 1. Otherwise, there's not excessive copy-ins happening throughout the code, even if you want to ensure data is present by adding that copy-in clause multiple times prior to each kernel. This is just the process that was taken here. And hopefully that gives you some ideas about navigating GPU data management in large scale models. So getting on to our final exercise we're planning to do. So we have this MPAS-A kernel extraction that we did. We're going to focus on this vertically implicit coefficients work that we're doing. So we'll be doing that acoustic computations and gravity wave computations that are in this subroutine here. This was extracted by Supreet Suresh here, and with further modification linked here within this workshop for you to work on. If you'd like to see the exact line from which this subroutine is sourced within the larger scale model, feel free to click that link, and that will take you to the exact source file where that's contained within MPAS-A. Otherwise, the kernel itself is within the workshop directory, which you can open up and see what's going on currently within this particular MPAS-A kernel. So in this case, we're resolving, not having you worry about data locality too much. That in the larger scale model, it has been addressed within the initialization and the MPAS pool routines. So we don't necessarily have to worry about that here within this particular kernel. So we're actually, in order to optimize the process of optimizing the kernel, we're just going to run, if you look at the code for the subroutine we extracted, we just randomize inputs for the data, and then and thus allowing us to just focus on optimizing the performance, not necessarily caring too much about the actual content of the data we're working on. Ideally, we should have like a validation tool for ensuring that correctness of the code is set, but we have not included this at this time. For larger code bases, as mentioned earlier, there are tools to automate some of that process. There's the Encode Gen tool for Fortran codes. There's also, if you have CUDA OpenCL codes, you might look into the kernel tuner program from the Netherlands East Science Center. And this just helps automate that process of extracting these kernels for you, and in some cases, even including a validation tool at the same time. At this point, let's get started with doing an exercise on the MPAS-A kernel. This will be similar to that walkthrough we just did earlier for the mini weather application and that final exercise. So essentially, currently in that subroutine, we have various kernel loops that are set using the ACC kernels clause. So that's to remind you the descriptive approach for OpenACC. And now we're going to try a more optimized and hopefully with better input from you programmers using the ACC parallel clause to encapsulate each of those compute constructs. So go ahead and open up that source file and look through each of those sections and start trying to apply different parallel compute constructs. You might first actually load and make the source file as it is currently, and then submit that executable to a GPU node on Casper to then see exactly what the current performance is just with the descriptive approaches of kernels. You can then look at the timing output, etc., to see exactly what is going on by the compiler in terms of the size of the grids and gain vector worker clauses. It's assigning for each of those compute constructs. And that can also help inform you of what might be a good approach to choose for the your own additions to the kernel subroutine. So as you make those edits, feel free to then edit the new timing you get on each of those changes you might make on a specific kernel. And then we can go from there. I'm just going to put up the slide here briefly before and just talk about these last few points. So across this process, and as we establish this process, and you might have your own better process for whatever model you might be working on, but nonetheless, it's just important to commit to a defined iterative development process, just so that you can navigate and have a clear thought pattern and plan of action for how you want to approach your GPU development project. It is always the case that making smaller and validated, you're making sure that each change you make is a small incremental change is actually correct and not introducing bugs. Those are easier to fix over time rather than if you try to port the whole model at once and then end up encountering a bug and then trying to figure out where that is. So making smaller incremental changes is the key here in terms of any process you might come up with. So to start with, you might say, as we're doing here, starting with the ACC kernels clauses, then adding ACC parallel. You can then notate over time what different performance you get for each approach. But nonetheless, it is sometimes the case that the kernels clause does achieve pretty significant performance results, and there might not be a need to do that manual optimization yourself. That is also just dependent on how expensive that particular kernel you're looking at. Nonetheless, lastly, just to understand that the GPU development process takes time and effort, but specific tools and techniques can drastically speed up development time. So hopefully, as we discuss this and you get some more practice in this space, you can develop the tools and tool suites in order to do this in a very effective process that helps ease your transition to GPU computing on Casper and later Derecho. So at this time, I'm going to pause the recording, and then we're going to split out to breakout rooms and let people work together on these different optimizations you're going to try out for the MPAS-A.